Today I will present our master thesis, our research called Improving Brain Tumor Multi-Class Classification with Semantic Features. This is the research of me and Yevgeny Pavlovsky from the Novosibirsk State University. So let me give a brief introduction of the problem and the main goals of this research. So basically, a brain cancer is a mass of normal cells that grow in the brain, and there are many types of brain cancer. Depends on where it arises from, and basically there are malignant and benign brain tumors, and malignant is cancerous and benign is non-cancerous. So even though some tumors are benign, it can also become dangerous because of the size and location. So by diagnosing the brain tumor type in the early stages, it will help the doctor to develop a quick and correct treatment plan for the patient, and the patient will have more chance to increase the survival rate. And the diagnosis of brain cancer will start with a doctor examine the MRI scans of the brain. And if a tumor occurs in the images, then the doctor will start to decide on the type of the tumor and then develop the treatment plan. And this process is usually very time consuming, and the interpretation of the image depends a lot on the experience of the doctor. So in order to improve the quality and the speed of this process, many deep learning or computer aided diagnosis system have been studied and implement to solve the problem. So the aim of this research is to first to examine the effect of the segmentation as a semantic feature. To first is to fine tune, and second is to transform classifiers, and second is to analyze and compare the result of the network on a private dataset and a public dataset. So as I mentioned in this research, we use two datasets. The first one is a private Siberian brain tumor dataset, which I will call the SBT from now. This is the collection of MR images from Russian people, from Russian patients, and the images will contain characteristic and pattern and structure specifically for Russian people. And this is private because this is not published for everybody. Not everybody can access to the dataset. And in this dataset, there are 363 cases identified by ID. And in this dataset, there are 4 types of brain tumor, you can see in the image. So the top rows is the some example from the dataset, which the first column is the first type, which is meningioma, and the second is the neurinoma type of brain tumor. They are benign brain tumor, and the third and the fourth columns are glioblastoma and astrocytoma, which are malignant tumors, and the bottom rows are the corresponding segmentation of the MR images. So this is the brain and this is the tumor. This is the segmentation, a semantic feature to its image. We also want to test our model with public dataset. So we use the multimodal brain tumor segmentation challenge 2020, or we'll call the PRAS 20 from now. This is a public dataset from a public challenge, and we use the training dataset. So in this dataset, there are 369 cases, and there are only 2 grades of brain tumor in this dataset, which is the high-grade glioblastoma and low-grade glioblastoma. So they are malignant, but they are different grade. And this is the example from this data set. The top row is the MR images, and the bottom row is the corresponding segmentation. So both data sets suffer from the imbalance problem. So for the SBT, the private Siberian dataset, we can see that the malignant cases are a lot less than the benign tumors, and similar to the breast 20, where the high-grade glioblastoma account for the majority of the case. And before feeding images into the neural networks, we need to do some pre-processing, because those images are acquired with different protocol, and then there will be some mapping. We need to transform the images so that we can compare the result more fairly. So for example, we need to change the number of slices to the first dimension so that we can use with the different third-party libraries. We crop the images in the center so that we can remove unnecessary data from the background. And it's, importantly, we need to normalize the values of the image and segmentation so that it all ranges from 0 to 255. And then we've done some removing edema from the segmentation, because we believe that the edema is just a swelling region. It's not the tumor, and it will confuse the model with those information. So we remove that from the segmentation file. And then we also remap values from the segmentation from the SBT, so that is the match with the plus 20. And finally, as we know that the 3D images contain a lot of slide of 2D image, and then not all 2D images contain tumor information. So we, to reduce the computation cost, we selected slices of that contain more than 163 pixels of the image. So the image on the right, you can see that the first columns is the original MR images. The second columns is the original segmentation, and the last columns is segmentation after being processed. So a lot of unuseful regions from edema is removed, and after remove, the segmentation contain values of 0 for background, 1 and 4 for two different tumoral structure. And then we also apply some data augmentation to increase the numbers of images and the variance of images, like flip the image with the probability of 0.5 in vertically, and then apply random gamma adjustment to change the brightness of the images. So to test the images from one simple network trained from scratch and one popular network with pre-trained, we create a simple neural network called the SimpleNet, which contains only 7 layers of 4 convolutional blocks, 1 flattened layer, 2 linear layer, and will output a vector of 4 values represent the probability of the brain tumor type. For the big architecture, we use the VGT with 16 layers in this case, and we only train the last layer with all other layer parameters are frozen. And because the last layer from the original architecture output 1,000 channels, but we only need 4, so we change the last one and we train on the last one only. So the overall process will be like this. On the graph on the right, we see that we have 2 data sets, SBT and plus 20. So the SBT and plus also need to be pre-processed, And then SBT will be split into training, validation, and testing, while all of the images from the past 20 will be used for testing. And the train and the validation will be split into five-fold cross-validation with the data augmentation applied. And then after training, two best model will be used for testing. And then the best model also be tested with the past 20 images. And the loss function used in this is the cross entropy loss. And we also apply several evaluation matrix to compare the performance of the models, like the accuracy, F1 score, sensitivity, specificity, and precision.
Excuse me, 2 minutes left.
Okay, thank you. So I will quickly go over the result. So basically compare models between with and without segmentation. We can see that from both scenario, model that provided segmentation outperformed the model with no segmentation. But VGG a little bit more outperformed with the simple net because VGG is deeper and is more robust. Even with no segmentation, it's also performed a little bit better. Compare the simple net and the pre-trained VGG from both data set. We can see that both models suffer, find it hard to distinguish between glioblastoma and astrocytoma, but it's very good at distinguish between the malignant and benign tumor. And the neurinoma is the tumor that can be classified the best. So in conclusion, we from the testing result, we can say that the brain tumor multi-class classifier perform more efficiently when the segmentation is provided, and why the pre-trained CNN have better evaluation metric on the private data set. The simple net is outperforms the deeper network that is trained for more general purpose on the bigger data set. So that's the end of my presentation. Thank you very much for your attention, and I would be happy to answer any question now.